Alright, let's press on. Right, yeah, I'm silly. I should have realised that we had never seen something like that before. So I'll quickly explain how you're meant to interpret that if it's not obvious. Right, so this is something else I'm going to use to talk about deletion, but if we've got an expression like that, current next data, what does that actually mean? Right, well, current, we assume current contains a pointer to a list node, or nowadays we don't call them list nodes, we call them struct nodes. Right, contains a pointer to a struct node that has these two values in it. Alright, it has the number 2, it also has a pointer to another node. Alright, so interpreting this, it's basically saying, alright, current contains a pointer. If I follow the arrow, that takes me to a node, and then I can deal with the fields in that node. So I take the next field, which is that value there, which also happens to be a pointer. I can then dereference that pointer, in other words, follow the arrow, go to a second node, and then I can access the fields of that node, and in this case I can access the data field, which is going to give me that 8. Okay, so it's following pointer change, and you can make them as long as you like. You can have current next data if you really wanted, and if you were sure that there were actually that many elements in the list. Here we guaranteed that there is going to be current next is not going to be null, because the part of the code that was dealing with that was explicitly checking current next is not equal to null. Okay, so this is the data value field in the node that's next from the current. This is the data value that's in the current node. Alright, hopefully that's not too confusing. Alright, so let me see, show this. Oh damn, I was... Well, let me see. Alright, I won't write all of these because I want to write them in two styles. We've already seen one style pretty much in the list0.c file. They had a whole lot of these functions written in, right, search we haven't seen, so I'll write that even though we can't test it yet. Now clearly this is standard list iteration, and we're iterating through the linked list. We're looking for a node whose data field matches that value. So you should be able to write that one pretty quickly. And I happen to have called all my list parameters capital L. Doesn't matter. They were called list in the other file. Okay, standard. I'm not writing it as a for loop. I'll be nice and write it as a while loop. That you should be able to just get that down pat, and whenever you've got a linked list problem, you can probably straight away type in those 4 lines, especially if it's a problem of iterating over a linked list. Alright, and generally the other part of such a thing is you're processing the current node and then you're going to the next node. Alright, so what's the processing here? We simply need to check, is the data value in the current node equal to the value val? And if it is, then we're done, we've found it, so the search is successful and we can return 1. So if current data is equal to val, alright, if we go all the way along the list and we make this check on each node, and that check never succeeds, clearly that means the val that we're looking for is not anywhere in the list. So if we ever exit that loop, then we know that we can return 0. So that would be an implementation of the search function. Is sorted basically the same as the is ascending function that I wrote just before, so I won't do that again. Similarly, insert, I will do that because our make node is different this time. Make node, blah, blah, blah. Right, where is it? Insert. Yeah. Struct node, node. So we make a new node and we store value in it. The other thing that we need to do is we need to set up the next field, which make node didn't do. So new next gets set to, what does it get set to? I hope that was L, that noise. Maybe it wasn't. And then we return new. Okay, new is going to become the new node at the start of the list. This node is linked to the node that was at the start of the list when this function began. Okay. So we simply create a new node to become the start of the list. Remember that this is returning a pointer to the modified list. So that's why we're returning the new node. And having created the new node, we linked it onto the rest of the list. Now, there's a diagram that describes this in the set of diagrams that I showed you last time. Right, append is basically scan to the last node and then attach the new node after that. Delete, all right, here's one that we haven't looked at yet. There's actually two ways you can do this. I'm going to show the one that I normally use, which involves 2 pointers. Partly that's interesting because it involves 2 pointers that move along the list. The other way you can do it with a single pointer and just keep checking next all the time. Alright, so I wanted to take a look at a diagram for this first of all. Alright, so you can forget about that. I might even just delete that. Okay, so we've got a list here. There's a pointer to the first node in the list and all the nodes are linked together, and we want to delete the node containing the value 7. Alright, so what are we going to do? Well, current is currently pointing at the first node in the list, and this prev pointer is always going to point to the node immediately before the current node. If we're dealing with the first node in the list, then we don't actually have a pointer before the current node. So we don't have a node before the current node, so we can set that to null. So you've got to imagine initially that's set to null. Alright, so what we're going to do, we're going to scan along the list, and these 2 pointers are going to move together. And what we're going to do on each iteration of the loop, we want to check, is this value the one that we want to delete? Okay. In this case, it's not, so we're going to execute these 2 statements here. So prev is going to be assigned the same value as current. Basically what that means is we make them both point to the same node. Right? So after executing that statement, that's the scenario we've got. And then current is assigned current next. Basically means take that pointer and move it to there. Right? And then we go through the loop again. Is this the value that we want to delete? No, it's not. So we execute these 2 statements again. Prev is assigned current, copy this pointer into this, which basically means we've set up that situation. And then current is assigned current next. We copy that value into there, which basically means that. So that's the current state of play. Alright, we check the value in the current node. Hey, it's the value we want to delete. Right, so what has to happen at this stage? This node has to be removed from the list. One aspect of that is freeing up the memory that it's currently using. the other thing we have to worry about is this pointer can no longer point there. It has to be adjusted so that it points there. Okay. So that's the final scenario that we want. We don't care about that pointer, we're freeing up the memory anyway, so that pointer is effectively gone away. So, how do we achieve this? How do we delete that? Well, deleting this is pretty straightforward, that's just free. Alright? And we're freeing the node that current's pointing to. Fixing this to make this point to here is simply a matter of copying this pointer into that location there. Okay? So then they'd end up pointing at the same thing, which is what we want. So taking a copy of this, putting it there is hopefully reasonably straightforward, but let's go and have a look at the code to do that. Basically what it is, it's saying we want the next value in the previous node to be equal to the next value in the current node. So we're just copying that pointer into there. So we'll see how that looks once we do code. But in any case, the first thing to do is to find the place where the item might be. Alright, so we need struct node current and struct node prev. And in fact I told you what they were equal to on that slide. So we initialize current to the first node in the list and we initialize prev to null because there is no previous node at this stage. Alright, and then we do a straight iteration across the list while current not equal to null. And remember, we may end up in that scenario, we may end up with current equal to null because the value that we're trying to delete doesn't appear in the list. So we're going to look all the way along the list and not find it anywhere. And so in fact, that's a scenario that what we do when we reach the end of the list is we say, all right, the value that we're trying to delete is not in the list, and remember that this function returns the new version of the list. Well, if the value is not in the list, the new version is going to be the same as the old version, and so we can simply return the value L. Now I was a bit slack here, I didn't actually check for the empty list case, but if you think about the empty list case, that just falls out in terms of those control structures. So if the list is empty, L will initially be equal to null, we'll assign null to current. Current is equal to null as soon as we check that loop test for the first time, so we'll go down here and we'll return the value L, which is null. Okay, so that works out fine. If you are worried about that and say, hey, I'd much rather have an explicit test, then you can certainly add that, although it's unnecessary. So you could do something like that. But as I said, the code as written is going to achieve that effect anyway. Alright, so what do we do? Actually, it might not be so simple, I might leave that. Alright, so anyway, one thing we need to do, if current data, and I'll fix that equals up in a minute. Then we probably want to quit the loop at that point and start fixing up the area around current and prev. And that's why we can't be quite so simple here. Alright. Otherwise, we do what I showed you on that slide is we move these 2 pointers, we move them along. So prev gets assigned current, current gets assigned next. So that's exactly what we put in the code. Alright, there might be 2 reasons that we get to this point. Always that's going to be the case if you've got a loop test and you've got a separate way of breaking out of the loop. I'll fix that. So always, in that scenario, there's always 2 reasons for exiting. One is that current might be equal to null. And basically what that means is we've got a non-empty list . Oops. We've got a non-empty list, so we just return that list unchanged. Otherwise, we have to do a little bit of work fixing up the area around the node that we've discovered. So the else part here is basically talking about this scenario here. We've got current pointing to the node containing the value we want to remove, and we've got prev pointing to the node before that. And at this particular point in time, the next value here is pointing to there. Right? So we want to modify this next value so it goes around that, if you like. Bypass it. I want that. I wanted this. Alright, so the first thing to do, bypass the current node. So the previous node next is going to be set equal to the next value of the current node. So we've got the node to be deleted, we've got the previous node, we've got the next node. So basically we're just saying this, the node to be deleted was pointing at that node, now we make the previous node point at that node. So that's what that does. And then the final thing to do is to free the current node. And we have to return something. Good point. What do we have to return? All right, well here there might be a couple of cases to consider as well. What if we deleted the first node in the list? We can't just... if we did delete the first node in the list, then we need to handle that case. Oh no, should have pointed that out. I've got a bug here. Alright? I can't just do that because it's possible that current is pointing to the first node, and in that case, previous would be null. So that's another scenario to handle. So this is handling the case So here we want to delete the first node, so let's look at how we deal with that. And this is a general case where we're some way along the list, we're not at the first node, so we're not deleting the first node, but that's all going to work all right. So here, the first node hasn't changed. All right. So if we're deleting the first node, what that means is the second node, current next, is going to become the new first node. And so we could say L equals current next. we still want to free the current node, and then we return L. Alright, so you look at those two cases and you go, they're both doing the same couple of things apart from the first line in each of these two cases. So it's not, it could be the last node in the list. Ooh, and that was a case I should have checked as well. So deleting a node somewhere along the list, not the first node. So, interesting case. What happens if we're deleting the last node in the list? Is this code down here going to work? You reckon? I think it might. If we're deleting the last node in the list, current is pointing to the last node, current next is null. Okay. So we're going to end up setting previous next to null. Now, if we're deleting the last node, the previous node is now going to be the last node in the new list, and it's correct that it's got the value null. If there's a node following the current node, then it behaves as I described before. So we're doing this bypass. Okay. The only trick is if we happen to be deleting this node, then we're copying this null value into there, and that becomes the new last node. Alright, now, one thing that we could do at this point is, if we really wanted to, we could take the free current return L, and we can put that down below. That's fine if you want to make the code a bit shorter. But often for all of these list scenarios, empty list is an important case. First node being affected is generally an important case. Last node being affected is sometimes a distinct case. And then you've got the general case where you're somewhere in the middle of the list, and that's what's being affected. Right, so we've kind of got all these scenarios explicitly. We've got empty list handled up here. We've got not in the list being handled here. First node being handled here. And middle of the list also actually handles the last node case. So if the node that we're affecting is the last node, that works fine. Alright, so that's deletion. You can see it's a little bit more complicated than some of the other functions that we've written. And I'm sure you can phrase this in different ways, and it turns out to be a little bit simpler. But that will do. Hopefully it works. Alright, so any questions on that? Oh, I don't like doing that. I think you're about to ask. Alright, next. And notice we don't need a return down the bottom because every case has a return. So that if has a return, that else if has a return, and that else has a return. So regardless, something is going to be returned. Alright, free list. Okay, that's an interesting one too. Once again, we're going to have to iterate through the list. This time, rather than looking backwards, we want to look forwards. So let's go back to my list diagram, which is here. So if we're deleting this list, we need to iterate along and delete each of the nodes as we go. Okay, so we're not going to have prev anymore, but I'll just leave that. So current initially points here. Now, one thing we want to do, we want to free current. Having freed current, we've thrown away this pointer. You should think of free as something that says, all right, you want to stop using a piece of memory that you've told me that you were previously using that you got from malloc. And what it does is just writes rubbish all over that memory. It marks it as being no longer in use, and it just covers it in rubbish. Alright, so if we do free current, then both of those values are gone, they've been replaced by rubbish. Importantly, we need to go on to the next node, and we've lost that next pointer that's been replaced by rubbish. So before we free the current node, we need to grab a copy of the pointer to the next node. So in this case, we can't, rather than current and previous, we need current and next. Oops, going back there. Alright, so start current, start next. Alright, current starts at the start of the list and next. And here's a good reason why we need to handle that empty list case specially. So if list is initially null, then there's really nothing to do. And since this is a void function, we don't return any. We don't return a value, we simply return. So we can write that. Right, we'll leave it with all that spacing in there. Okay, so now what we need to do, we need to scan through the list, and we need to do that until we've examined all of the nodes. And so we still want to go on current. It's not equal to null. And maybe we don't want to go beyond the last node, but we'll see how that's going to work out in a moment. Alright, so remember the first thing we need to do, grab a copy of that next pointer because we're about to destroy it, and then do free current. And then go current equals next. Okay, so the only reason we need to do this little trick is that this thing here wrecks that value. So we need to grab a copy before we wreck it, and then we can use it down here. And that's it. So that scans along the list, freeing each node as it goes. Any questions on that? Must be explaining it well, or else so poorly, but no questions are cropping up. Alright, so I think that's all I'm going to do for that one. Most of the others you should be able to write yourself based on the code in list0.c, because it's essentially the same, just some of the names have changed. You know, we've got L instead of list and so on. Easy enough to do yourself. Alright, let's take a look at an alternative viewpoint on lists. So another way of looking at lists is to take a kind of recursive view. So a list consists of a head, which is the first element, and the rest of the list, which is itself a list. So a list is composed of a smaller list is composed of a head and a smaller list, which is composed of a head and a smaller list, which is composed of a head and a smaller list, all the way down till we got nothing left. So thinking about lists in that way is actually leads to some quite nice solutions to the functions that we just implemented. So let's take a look at them. So I will just save that file. And I will grab a copy It's very subtle there, there's an underscore sitting at the start of that. But anyway, okay. So let's go back here, open lists.c. So here's a new version of list.c which has had pretty much all the code taken out of it again. Alright. Okay. Let's start with length. So how long is a list? And now we've got to think of things in terms of a head and a tail. How long, and also the base case is always going to be the empty list. So here we end up being very explicit about that base case. How long is an empty list? I would have thought it's 0 length. That's fair to me. If a list is not empty, how long is it? Well, it's definitely got a head and then it's got a tail. How do we work out how long the tail is? We can recursively call length, because the tail is just a list. And so the total length of a list which is not empty is going to be 1 for the head of the list plus the length of the tail, which we can get by going to the next node, because you can think of the next node as being the start of the tail of the list. And that's it for length. So empty list, length 0, not empty list, as list has 1 node in it, so we count that and then work out how long the rest of the list is using a recursive call to length. And this kind of structure follows through all of the other functions, so they end up being quite nice. Alright, so let's take a look at show list. If the list is empty, there's nothing to show. So I'll write that explicitly. Actually, there might be. I think the original version of show list prints a new line at the end of the list. So if the list is empty, we've either got an empty list or we've reached the end of a non-empty list and we want to print a new line character. Otherwise, we want to print one thing you might notice about these solutions is they don't involve a lot of extra variables being defined within the function. So we display the first element and then we display the rest of the list recursively. How do we display an empty list? We simply write nothing, we write a new line character. A non-empty list, we display the head, which is L data. How do we display the rest of the list after the head? Well, we make a recursive call to show list. Done. Jump in with questions if any of them are not understandable. One thing that might be wondering, I'll take a look at it in this context. How do we eventually stop? Well, if we keep going L next, L next, L next, L next, eventually we're going to be calling length on the last element of the list. And when we do length L next, the last element has a next pointer of null, so we're always eventually going to reach this point here. So the thing will always terminate, and of course when we return 0 for the empty list, that gets added on to all of the other ones that we've incorporated into the sum along the way. And of course adding 0 doesn't change anything. So all of these things eventually terminate, assuming that the last struct node in the list has a next value which is null. Alright, so So searching, one thing, once again we handle the empty list. Is a value contained in an empty list? No, it's not. So we can just check if the list is empty, then clearly val is not in it. If the list isn't empty, then we've got a head. Maybe the head contains val, so we can check that. And if that's the case, then we've definitely found the item we were looking for, or the value we were looking for in the list. Alright, so empty list case is handled, finding the item we're looking for is handled. What if we didn't find the item that we're looking for as the first item in the list? Maybe it's in the rest of the list. How do we work out whether it's in the rest of the list? Well, the rest of the list is a list. We've got a function to search lists. So we can simply recursively call search on the rest of the list, and whatever value comes out of that is whether the item is in the list. Okay, we know it's not the first item. Maybe it's the second, third, fourth. Maybe it's somewhere else in the list. This recursive call here is going to tell us that. Okay. Any cool questions on that? I really like these things. A lot of them kind of look like magic. How does this actually work? It's too simple. Can't possibly work. But it's just a matter of thinking in terms of the head, the tail, and I guess the base case of an empty list. Alright, is sorted. Let's adopt the same strategy. If the list is empty, we decided before that it was sorted. The other thing to notice about these two is the things that are controlled by the if are generally just a single statement, so we don't need any braces. If you insist, you can add the braces everywhere, but not necessary. So it would have worked perfectly well the way I had written it before. Right, getting back to this. Alright, so an empty list is sorted. A list with one element is sorted. We could handle that as a separate case, or we could bundle it into that test there, but let's handle it as a separate case. How do we know it's a list containing a single node? Well, the head element has a next value which is null, so therefore it must be the only node in the list. And if that's the case, once again, it's a sorted list. So we've handled two cases: empty list containing one element. The only other thing to worry about is, what about if the value in the head is greater than the value in the next element? We know there must be a next element because we didn't go to that case. And this is where we use our double redirection again. So there we found our counter example. We found two elements that are out of order. And what else? Well, the first two elements must have been in order, so we've got to worry about the rest of the list, whether that's sorted. And so we simply, how do we work out So the first two elements were sorted. How do we work out whether the rest of the list is sorted? We got a function to do that. So we can recursively call that.
It should be is.
Oh yeah, thanks. Yeah. So got to use the right name. Oh, did I call it is sorted everywhere? I think I did. Alright, so is sorted done. Insert. Oh, how difficult can this be? Alright, this one kind of looks a little bit like the previous version of insert. So we need to make a new node. And we stick the value in it, and then we say new next points to whatever the first node in the old list was, and then we return new as the new first node in the list. So that's exactly what we had before. Append. Well, we can think about the empty list case. If the list is empty, we could write make node new next, or we could just be lazy or sensible and make use of the function that we've already got that will handle all of that. So we insert the value at the start of this empty list. Alright, so that's the simple case. Otherwise, we want to add it at the end of the list. Can we use recursion to get our way down the list? I reckon we can. Right, if the list isn't empty and we're appending, then let me think how to phrase this best. Right, what we really need to do is check whether we're at the end of the list. We're at the last node. And I guess you could kind of think of that as the case of a one node list. How do we add an element to a one node list? Well, we create a new node and we link it onto that single node that we've got. And I reckon that we might be able to do that like this. Yeah, it looks kind of plausible. So we pretend that we're inserting into an empty list because we've got this node, this single node that's going to hang at the end, and we take the current last node and we make it point at that. And that allows us to just return L, so obviously we're going to need braces here. Otherwise, we're not yet at the end of the list, so we need to append the node and then return the list. We need to append the node in the tail of the list and then return the whole list. So how do we append a node on the list? Well, we're writing a function to do that. And because we know L is not the last element in the list, and even if it was, oh, maybe I've over-committed this case, we also return L. So once again, we've got return L in both of those branches of the if. We could have taken it out, which meant we could have got rid of the braces. Right, so empty list case, we simply do an insert. That's going to work. If we're at the last node, we can do an insert into a pretend empty list and then attach the node that we just inserted, which creates a singleton list to the last node of the existing list. And that becomes the new list that's got something appended to it. Otherwise, we can just recursively call append. We'll chain our way along the list and eventually add it to the last node. But and then we return the value of L. All right, so that's appending. Yeah, if I wanted to make it shorter and simpler, then I'd do it like this. I like having those cases that have only got one statement. So it's just exactly the same, because if you remember, both of these cases did a return of L. Delete. Alright, might take a look at delete next time, although it's surprisingly similarly kind of simple. I'll just quickly do free list. If the list is empty, then we don't need to do anything, but I'll explicitly put in an if. If the list is non-empty, then we can get rid of the tail and then get rid of the head. And we're done for that. Right, the difference between that and the version I wrote before is that the previous version with the while loop deletes the first node, then the second, then the third, then the fourth, and so on. This one actually deletes from the back. So you eventually reach the end of the list and you just do a return there. But when you get to the last node in the list, you call free list L next, that's null, so we're just going to return straight away, and then we delete the last node. And then the free of the head of the list always happens after we've deleted all of the tail of the list. So you can see that we delete the last node first, second last, third last, and we gradually work our way back. And the very last thing that we delete is the first node in the list. So, like I said, the order's different, but the overall result is the same. Alright, that'll do. I'll type up delete and stick that in there, but it's kind of similar to, vaguely similar to append.